So I wanted to do a little like review of the online video, just a few quick examples, make sure everyone's on the same page. Go through Newman projections, and then get us up to where the next video is going to start. So let's talk about melting point. So the easy thing with melting point is that the more carbons you have in the chain, the higher your melting point. So here, hexane has the highest melting point, ethane the lowest, and butane in the middle. Right. Now there is a thing where the even numbered carbon chains and the odd numbered carbon chains have two like parallel melting point tracks, and they don't overlap. So I'm not going to give you something that has an even number of carbons and something that has an odd number of carbons, because like, well, you could do like, I don't know, ethane versus nonane. I don't expect you to know that, well, pentane's boiling point is a little bit higher than hexane's, or melting point is higher than hexane's, or whatever it is. So I'm always going to just give you all evens or give you all odds. So there's the number of carbons. Oh, we're not in airplane. Another thing with melting point is the number of branches. More branches equals a lower melting point. So right, if everything has the same number of carbons, right? These all have 6 carbons. So you're just looking to see what has the least number of branches. That's going to have your highest melting point. So that would be like A. C has the most branches, so it would be the lowest, and B would be in the middle. Right? And that's because right, melting point and boiling point are really measuring how well the molecules fit together, right? And so it's really easy to fit molecules together when they're straight and they don't have any branches, right? They fit together much easier. It's the Tetris example, right? Tetris would be really easy if it was just all the stick, right? It'd be super easy to fit everything together. But when you start kind of like making the stick irregular, right, then it becomes harder to put the blocks together. And it's the same thing with the molecules. As the molecules have more bumps and more substituents, they become harder to fit together. Boiling point, we don't have the same odd even issue with boiling point, so we can just go by whatever molecule has the most carbons should have the highest boiling point when we have like a straight chain. So which one of these is going to have the highest boiling point? Which one? B. B has the lowest because it has the least carbons. C will have the highest because it has the most carbons. And A will be somewhere in between. The same thing holds for branching. Right, so these are all 5 carbons. More branches equals lower melting point, less branches equals higher melting point. So what has the highest melting point here? B. What has the lowest melting point? C, and then A is in the middle. There you go. The other, yes, ma'am. So, like, the number of substituents off the main chain. So here is one branch, one substituent. This has two substituents. So it's just the number of substituents coming off the main chain. The other thing that comes up with boiling point, that comes up less with melting point, are rings. It's still on boiling point here. It's going to be green this time. So rings are easier to stack together than straight chains. So they have higher boiling points. So if you have something that is like this, I just happen to put this in order from high to low. So this is A, B, C. So the ring has less degrees of freedom, so it's kind of like more of a fixed shape. So it's easier to stack together than the straight chain, and the straight chain is easier to stack together than the chain with one substituent on it. So I won't mix up numbers of carbons too much, but like for boiling points, you can, like let's say you had, We'll make this boiling point again. Right? Which one of these should have the highest boiling point? C, right? So, yeah, but anyway, so you know that between A and B, B should have a higher boiling point than A, right? And now you're comparing a 4-membered ring and a 5-membered ring, and since a 5-membered ring has more carbons, it should have a higher boiling point. All right, so the last thing is water solubility. And the big thing here is the more polar functional groups you have, the more water soluble your molecule is. So let's say you had this versus wait, I got one too many carbons in there, sorry. Versus this. A, B, C, low to high. So which one of these would have the highest water solubility? B, because it has 3 polar functional groups, even though that NH2 looks like it got like hit by a bus. NH2, slightly better, right? So B has the highest water solubility because it has 3 polar functional groups. A has the lowest water solubility because it has 1, and C is somewhere in the middle. So there's more to that video, but this is kind of like the quick flyover review. Make sure everyone is at least has like the same basis. Okay, so I want to get back to Newman projections. All right, so we left off on doing Newman projections, the easiest Newman projection possible, which was ethane, right? And here's ethane in the Sawhorse conformation. right? And we have two possible conformations. We have the staggered conformation. And we have, we'll rotate it around. I like to move the back carbon, or rotate the back carbon. And then we have the eclipsed conformation. All right, so those are the two possible conformations that ethane can exist in. Right. So we are looking at, here's my crappy eyeball. I'm looking at this carbon right here. That's that carbon right there. So I can't see this bond between the front carbon and the back carbon. All right. So I want to talk a little bit about the energies of these, but that requires me to go to another slide. So for this staggered, this is the lowest energy conformation, right? So that makes sense. The hydrogens are as far apart from each other as they can possibly be, so they don't bang into each other. So, and then the eclipsed is the high energy conformation. Right. The thing that makes staggered, that staggered is the lowest energy conformation, right? That means it's the most populated. So if you took a picture of every ethane in the world, most of them, like 70, 80, 90% of them would be in the staggered conformation, and then a smaller percentage, 10, 20% of them would be in the eclipse conformation, right? Because it's just easier to be in the staggered conformation because it's lower energy, right? The reason these are high energy is the hydrogens repel each other. Right? So I'm going to go back a slide real quick. So if we think about what an atom is this really concentrated small area of positive charge that then has a cloud of electrons around it, right? So the vast majority of an atom is electron cloud. So when the groups, in this case the hydrogens, get close together, their electron clouds start to bang into each other, right? So you got these two negative clouds that get closer together and then they push apart, right? So if you learned nothing from like physics in high school, you learned that like charges repel each other. So you got two big negative charge clouds, they come together and they push apart, right? When they repel, that's called a steric interaction, right? I'm going to define steric interaction, right? So the hydrogens repel each other, it's a steric interaction. So steric strain / interaction is when atoms in a molecule get close together and repel. Right? So as you move atoms closer together, because they have that negative cloud around them, they push apart. So that's called steric strain or a steric interaction. Sometimes it just gets shortened down to sterics. Right? In a Newman projection, the particular type of steric interaction is or steric strain is, we're going to go to another slide here. In Newman projection. Strain is called torsional strain, right? So again, we're going to go back to like physics, right? Torque is when you apply a force that makes something rotate or something turn, right? So when these hydrogens get close together and they push apart, they're applying a force that makes the single bond between the two carbons rotate. So I'm going to jump back for a second. Right, so when you get to the eclipse conformation and those hydrogens overlap, they're pushing each other apart, and they're pushing themselves apart so it rotates back to being a staggered conformation. So the force that's being applied says wants you to rotate around that single bond. So it's causing a torque. It's causing that bond to want to turn, which is why it's called a torsional strain. Get back over here so you can actually write stuff. All right, so if ethane's the easiest Newman projection, kind of the next level up in difficulty is doing butane. So we're going to do butane's Newman projections. So butane looks like this. We're going to draw 6 different Newman projections that work all the way around that single bond. So having that single bond rotate all the way around. So, you know, if it was a normal year, I'd have like 8 feet of whiteboard to get all these on at the same time. I've got a small iPad screen, so we're going to have to use multiple slides, which is not ideal, but we'll make it work. So again, crappy eyeball, we're looking at this carbon back to this one. So if we number them, 1, 2, 3, 4, we're going to do a Newman projection. From C2 to C3. So we're going to do our Newman projection with carbon 2 in the front, looking back to carbon 3. So carbon 2 right here, what does carbon 2 have on it? It has the methyl group that is carbon 1. And then it has a hydrogen and a hydrogen coming off of it. So those hydrogens aren't shown on carbon 2, but you know they're there because you can see the 2 bonds, and then the other 2 bonds have to be hydrogens. Then carbon 3, we can't see carbon 3, we just see the things attached to carbon 3. So you've got the methyl group, a hydrogen, and a hydrogen. Right? And you can see the way I started, right? So this is the bond I can't see. Carbon 1, this methyl group here, and carbon 4, they're on opposite sides of that bond. And in my Newman projection, this is carbon 1, this is carbon 4, they're on opposite sides of the Newman projection. This is a staggered conformation. Oops. Staggered. But it's a special kind of staggered conformation because the 2 largest groups are as far apart from each other as possible. So this is called anti-staggered. So there's 2 terms. There's anti-staggered that we're going to see, and then we're going to see fully eclipsed here in a second. I only really ever have you worry about using those in things like butane that are really simple. Anything more complicated than that, I would just be happy with you saying that this is a staggered conformation, and you'll see when we do more examples what I mean. So we're going to rotate here. What I like to do when I rotate is I like to leave the front carbon exactly how it's drawn, and then just think about grabbing one of the groups and rotating it around. So we have that front carbon's unchanged. Now I'm going to rotate the back carbon a sixth of a turn. So that's going to move this methyl group behind this hydrogen behind this methyl group, and this hydrogen behind this hydrogen. So now I've gone from the staggered conformation to the eclipsed conformation. I'm going to rotate again. Again, I'm going to grab a group on the back carbon and turn it a sixth of a turn. Front carbon stays the same. And this is a staggered conformation, but it's a staggered conformation that has a special name, because of course it does. This is a gauche conformation, G-A-U-C-H-E, right? A gauche conformation occurs when any two non-hydrogen groups are side by side. So the reason this is gauche is that this methyl group and this methyl group are beside each other. When they are beside each other, we get a steric interaction. Oops. So hydrogens are small. They can be side by side and not bang into each other, right? They only bang into each other when they're right on top of each other. For gauche interactions, methyl groups are way bigger, right? There's a carbon with hydrogen sticking off of them. So they're big enough that when they're side by side, they bang into each other. They don't have to be on top of each other. They can be side by side, and they get an interaction. So that is a gauche interaction. So this steric interaction is called a gauche interaction. Oops. A gauche interaction, right? And we call that whole conformation gauche. G-A-U-C-H-E. There you go. We can keep turning, right? We're going to keep going this way. And then we're going to have an eclipse conformation. This is a special version of the eclipse conformation. It's called fully eclipsed because the two largest groups are on top of each other. So this is fully eclipsed. Now I'm going to keep going this way. And now I'm going to end up, little arrow, with another gauche. Hey, letters, cool. Another gauche conformation. Keep going again. We're going to get an eclipse conformation. And then if we keep going, sorry, this H, I should make that clear. This H is on the front carbon. This is the methyl group on the back. And if I keep going, I end up back where I started. And I don't know why I said started weird there, but I did. Right, I end up back at that anti-staggered conformation. Right. So I'm going to run back for a second to the beginning. Brace yourselves. Every if you're asked to draw every possible Newman projection that you can for a molecule, you should think automatically that you should draw 6 conformations, right? Each of the Newman projections that we drew is a sixth of a turn, right? I went from anti-staggered to eclipsed. I moved that methyl group a sixth of a turn to get to the eclipsed. I moved it a sixth of a turn to get to a gauche, a sixth of a turn to get to fully eclipsed, a sixth of a turn to get back to gauche, and a sixth of a turn to get back to eclipsed. And then that last turn gets me back to anti-staggered. So there are 6 possible Newman projections for a molecule. Right? Now, sometimes there'll be less. So in the case of butane, 2 of our conformations are the same, right? But don't go like trying to be all fancy and trying to figure that out. Just draw all 6. The most important thing for Newman projections for you to get them right is the first step, right? If you do a good job, or if you're good at translating your skeletal structure into your Newman projection, you shouldn't then mess up any of the other Newman projections, right? Because you're just working your way around. You're just kind of thinking about grabbing a group and using it as a handle to turn a sixth of a turn. If you mess up the first structure, you end up messing up every other structure because you don't have your groups in the right place. So you need to make sure that you take the time to get your groups in the correct position. I have an answer. It's my job. So I got asked here if it mattered which side you put the hydrogen or the methyl group on when you're in the eclipse structure. No. So the thing I try to do, and this is just me being a weirdo, is I try to, like, if I have this a little bit past the group it's behind, I put the next one past, because I think of them as like they're actual physical objects where you've got this and you're rotating them, right? So if my ring finger is in front, my next finger should be in front. I'm not going to have them like one in front, one behind. I'm thinking it was like an actual physical object that's moving. But I don't care. As long as it's clear that they are like behind each other, that is all that like I care about. Is that it's clear. So if you did something like, right, you were like, hey, I have this, and you've got your methyl group this side, your hydrogen this side, and your hydrogen over here. I don't care. It's clear that they are super close together, so they must be eclipsed. But I always try to draw them the same because I'm thinking of them as an actual physical thing moving. But, yeah. Yeah, as long as you can tell. And, like, yeah, so it's one of those things where, right, if you put this hydrogen, like, over here, now I'm like, is it kind of screwed up? Or were they trying to say it was eclipsed? So as long as it, like, clearly tracks, that's the important part, is that it makes sense all the way around. Never kind of give me, no pressure, only a minute left. Never give me something where it's kind of like in between two things and you want me to kind of guess where it is, because I'm just going to assume you didn't know what you were doing. So just make sure it's clear. Okay, if there are no other questions, I'm going to stop and jump to the next set of little whiteboard sheets. Okay, so I want to show the energies of these different conformations. So I have a little graph here. Our y-axis will be energy, and our x-axis is kind of degrees of rotation. Right, and it's going to look something like this. I'm going to do my best to fit all the pictures in here. That's pretty good. All right, so this lowest energy conformation, this is our anti-staggered conformation. So this is anti-staggered. Now, the next conformation up in energy is the eclipse conformation. Well, that one got really ugly really fast. Right, so we have our eclipse conformation. Right, so it's higher in energy. Then we have the gauche conformation. So it is less stable than the anti-staggered, but more stable than any eclipse structure. The highest energy conformation is the fully eclipsed. We've got gauche here, fully eclipsed. There. Right, this is just eclipse. Right, so we go low energy, higher, we come back down for the gauche, we go way up for the fully eclipsed, and then we work our way back around with gauche, then back to eclipsed, back to eclipsed, and then we end up back down here at anti-staggered. So this graph wraps its way around. So we start out down here, we work our way around, we get to fully eclipsed, and we come back down to our anti-staggered. So we go all the way around. So, got a little bit more time, but not much. I am never going to ask you to just reproduce the Newman projections for butane, right? Butane is kind of the jumping off point. What we're going to spend a lot of time on Wednesday doing is I'm going to just give you a molecule and we're going to work through how you draw all of its possible Newman projections, right? But because I want you to watch the slide set 7 to 11 videos, I'm going to jump ahead just like a slide and get to slide 5 and start going over rings so that those slides make sense. And then on Wednesday, I will circle back and do a bunch of Newman projection problems so you don't feel like you got gypped. So I'll finish up slide 4 on Wednesday, but I want to get to the cycloalkanes now. All right. I'm going to talk about cycloalkanes. All right. So an sp3 carbon has an ideal bond angle of 109.5 degrees. So basically what that means is if you have a carbon that has 4 bonds, or 4 single bonds, all of those bond angles want to be 109.5 degrees. That is where there is absolutely no strain present in the molecule, right? Or in those bonds. There's a phenomenon called ring strain, which is also known as angle strain. Oh, man. That results from carbon needing smaller bond angles, right? So if you are, ideally carbon wants to be 109.5, but if due to the structure of the molecule, carbon has to bring those bonds from far apart to close together, it causes strain, right? The electrons in those bonds get too close together, and just like the hydrogens in the Newman projection, they want to push apart, right? So kind of the biggest example of this is cyclopropane. Let's say we have a cyclopropane, but let's say it's not a cyclopropane. Let's just say this is an equilateral triangle and you're somewhere between 8th and 10th grade. And you remember, what is the angle that you want to have in an equilateral triangle? 60 degrees. 60 degrees, right, if this is just a triangle, is really, really far from 109.5, right? So for us to make a cyclopropane, carbon really, really, really has to push its bonds closer together than it wants to. And by bringing those bonds closer together, it builds up strain, right? You can think of carbon just barely holding that bond together. So when we draw our bonds, right, when we draw molecules, right, we know that the end of lines are carbons. The lines are actually, in a sense, drawing where the orbitals, where the electrons are that make those bonds. But cyclopropanes are the angle is so small, carbon can't actually put its orbitals to make the bond on the lines we have drawn. The orbitals in a cyclopropane look like this. They kind of hang out outside the bond, a little back here, right? So instead of having our electrons on that line that we draw, there's the orbitals that make the bond are out here. They're kind of bent. These get called Walsh bonds / banana bonds, right? So the orbitals, instead of like going together straight and like hooking together really strong, they're bent. And they're just barely holding on because of how close you have to get for how small the carbon's bond angle has to be. It can't actually get to 60 degrees. The orbitals don't end up being that close, right? But there's a lot of strain in a cyclopropane because of how small the bond angle is. And cyclopropane, not only does it have the most ring strain, it also is flat. So once you get past cyclopropane, none of the rings are flat. They all have some sort of three-dimensional shape. Cyclopropane is just effectively a triangle or triangle-like thing that is perfectly flat. All three carbons are in the same plane. But as the rings get bigger, they take on a three-dimensional shape, which helps get them closer to the ideal bond angle. So we're going to look at two in particular. We're going to look at cyclopentane, and we're going to look at cyclohexane. Right, so cyclopentane. So if cyclopentane were flat, I do believe this bond angle would be 108 degrees, right? If it was flat. But, and cyclopentane is really close to being, or 108 degrees is really close to being 109.5, so there's already a lot less strain in this. But cyclopentane doesn't look like this. It's just not a pentagon flat in the world. It looks like this. No, not like that. We've drawn it poorly. Let's try again. I'm thinking too much. It's in what's called the envelope conformation. Right? Right? So you've got 4 carbons that are in the same plane, and then one carbon that sits above, right? I have this break in this bond here, so like right here, there's this little hole, because I'm trying to kind of denote perspective, where this bond right here is in front of, pick a new color, is in front of this bond here, right? So they sit in front of each other, right? I'll do it like this. So, right, you can't see all of my finger behind this finger because the front finger is blocking it, right? So there's kind of a gap. That's what that like break is trying to denote, that, hey, there's a gap because you can't see that, right? But you have these four in the same plane, one above. It kind of looks like an envelope. Envelopes are the things that your grandma sends you money in. I know you guys don't use envelopes, right? Right, but you could see your grandmother licking the orange carbon and then folding it down, right? It's an envelope. Now, the thing that kind of goes wrong with the envelope is that you have all of your hydrogens. If you were to draw a Newman projection, all the hydrogens are eclipsed, right? So these two hydrogens right here, this you can see, they are right in front of each other. So every hydrogen on the envelope conformation of a cyclar pentane is eclipsed. So every Newman projection you would draw is high energy. Now, the thing that we really care about, the thing that we're going to spend the most time doing throughout the semester, are cyclohexanes. Right, cyclohexanes, they have really interesting structures, right? So I do believe, again, that if it was perfectly flat, it'd be 120 degrees. 120 degrees is pretty far from 109.5. But, again, cyclohexane doesn't exist as just a flat hexagon. It exists in something called the chair conformation. I'm going to draw this. I'm going to draw it slow and see if we can follow along. So you do this, kind of like a V, and then ideally you want to draw two horizontal lines that are the same length. Right, and then you're going to draw again, and this is called a chair conformation. Right. So if you're not quite seeing the chair, there's a person on the chair, head goes at the top, feet at the bottom. They could have like a little book, just relaxing, right? It's a chair. Now, the ideal thing about the chair, right, or the good thing, as I draw it again, is the bond angles get really close to 109.5. The bond angle here is 111 degrees, right? So pretty much no angle strain, or very little, because you're almost at the ideal carbon-carbon bond angle. And the groups, I'm just going to draw two here. If any Newman projection you draw, all of your hydrogens, these are all staggered. Right, so there's no eclipsing interactions to raise the energy of the chair. Seem reasonable?